Okay, all set. So we'll turn it over to the group and let them share with us their design.
Alrighty, hello everybody, first off, and welcome to our final design presentation. My name is Edward Shelikoff, and we are EML4501 Group 15. Today we are going to show you our design, the Automated and Incubated Microplate System, or AIMS for short. Next slide, please. So our group was commissioned by the UF Biofoundry to design a semi-autonomous microbioreactor that can interrogate cellular properties in a larger capacity than the products that are currently available in the market. The goal of this microbioreactor is to increase cellular throughput while minimizing human interaction. The customer, the UF Biofoundry, provided us with 35 different needs that they wanted the final product to have. They also included a few try-to-haves that were not as important, but it would increase the product's value in their eyes. In this presentation, we will cover first our hedgehog concept with a quick product overview, and then we will progress to in-depth descriptions of each of our subsystems, as well as their technology readiness levels and unique features. Lastly, we will break down the final cost of our design and give our argument for why our design should be selected for prototyping. Next slide, please. So in order to create a cohesive product of this scale, we needed some fundamental direction to take our design. And this direction took the form of a hedgehog concept. A hedgehog concept is the intersection of these three important questions. What are we deeply passionate about? What can we be the best at? And what drives our economic engine? As individuals, we are each passionate about different things. But as a group, and eventually, hopefully, as a company, we are passionate about bringing the most robust product to market that will allow our customers to use their time more efficiently. Now, what do we believe that we can be the best at? We believe that we can and should be the best at reducing user involvement as much as possible for microplate culturing. We believe this will save our customers countless hours and increase our product's value. In other words, the researcher's time is their money. Lastly, our economic engine is driven by creating value for the customer and increasing profit per customer through bulk purchases, as well as word-of-mouth recommendations within the close-knit scientific community. The answers to these three questions led us to a hedgehog concept of autonomy/automation of microplate culturing routines. With the major design decisions that we made throughout the design process, we returned to this hedgehog concept for direction. Next slide, please. So shown on the screen is a final render of our design, as well as its overall dimensions. As you can see, it has an overall height of just over 1 meter. So this device is fully accessible to anyone within 2 standard deviations of the average height for men and women. So a little bit about our design. It consists of a liquid handling system with 3 axes of motion. This subsystem consists of a pneumatic gripper, an automatic pipetting system, and an 80/20 aluminum support frame. The pneumatic gripper allows the system to deliver the well plates to their incubation and monitoring system. And because of this, our design can accommodate well plates size 6, 24, 48, 96, deep 96, and 384. It can also accommodate 15 and 50 milliliter conical tubes. In order to efficiently control the environments of the cells during culturing in these well plates and conical tubes, we created 2 separate incubation systems for the well plates and conical tubes. These systems include a gas controller to inject and regulate the concentration of nitrogen, oxygen, carbon dioxide, methane, and hydrogen, and can capture any effluent gases. Now, the customer asked that this design run from a 120 volt AC electricity from a standard wall outlet with a 15 amp breaker, or a total of 1800 watts. And through the addition of the power used from each part of our design falls well below this maximum power. As shown on the slide, the base of our design is open to air. This allows for easy cleaning and microbial replacement, as well as replacement of any well plates that were just used, or cleaning of the waste bin. Now, the customer also required a minimum factor of safety of 1.15 for the design, and we performed finite element analysis using ANSYS on the vertical pieces of the 80/20 frame of the liquid handling subsystem. And this showed a factor of safety well above 1.15. And we also ensured that each surface that contacts the cell cultures are non-porous and non-reactive. Because of these design decisions that we made, these factors, we expect our design to have an operational lifetime of well over 10 years with correct and responsible use. Now for a deeper look at the liquid handling subsystem with Ariana. Next slide, please.
The liquid handling subsystem is tasked with adding and subtracting fluid from well plates and testing tubes, as well as transporting well plates to the incubation and monitoring system. This system consists of a gripper to transport the well plates and automatic pipettes to handle the fluid addition and subtraction. The liquid handling system has 3-axis motion to accommodate for well plates and testing tubes of different sizes. The motion of the gripper and pipette is programmable for specific experiments. The whole system is supported by an 80/20 frame. So why 80/20? 80/20 was chosen for a couple of reasons. First, it allows for the modularity of the whole system and ease of assembly. The user can actually change the assembly to accommodate a specific lab space. A lot of our systems depend on the 80/20 frame. My teammates will go over some of those systems later in this presentation as well. Also, an 80/20 frame allowed for the use of off-the-shelf parts to be incorporated seamlessly. For example, the linear rails and the linear bearings are created specifically with use for 80/20. So we were able to justify the use of off-the-shelf parts for most of the linear motion. Next slide, please. Our design incorporates both a gripping system and a pipetting system in order to fully automate the liquid handling aspect of the product. This entire platform will move around the board to perform different tasks. The pipetting system consists of 2 off-the-shelf pipettes that can hold and dispense different amounts of fluid. The user can choose which pipette to use for each experiment, or both if needed. The pipettes can pick up and dispose of pipette tips, which are made to be non-reactive with cell cultures and chemicals. And since this entire system can move around the board, the pipette tips can be discarded in the waste area of the device. I will elaborate on the pipette specifications later in this presentation. This design also features a gripping system. The gripper has the capability to grab well plates and move them around to different locations in the device, like the incubation and monitoring areas. It can be rotated by a stepper motor to change the orientation of the well plate as well, just to be able to fit all those different components of the design. Next slide, please. The single channel automatic pipettes are from a company called Opentrons. Our design uses 2 of these electronic pipettes, each with a different volume range to acknowledge the customer needs. The P20 has a volume range of 1 microliter to 20 microliters, and the P1000 has a range of 100 microliters to 1,000 microliters. We chose to sacrifice processing time to reduce cost and have more accurate fluid exchange. If the customer needed to dispense greater volumes, the electronic pipettes could always make multiple passes. The gripping motion is controlled by a pneumatic angle gripper. This pneumatic gripper can open to 30 degrees and -10 degrees. This is able to grasp well plates and even some of the lids for the other systems. Next slide, please. Our device is able to automate the liquid handling process for so many different sizes of well plates and tubes because of the 3-axis motion control. The gripper and pipette are raised and lowered using an electric actuator, which can travel up to 6 inches. This allows for the gripper to be able to pick up well plates on the base, as well as lift them up to be placed in the monitoring and incubation system. The X and Y axis motion is controlled by a stepper motor and a belt. The motor has a 1.8 degree step size, which translates to approximately 1 millimeter linear step size. And this small step size is enough to accurately process each well in a well plate, even the smallest difference between the welds, which is the 384 weld plate. Now Joanne is going to walk you through the base subsystem and the user interface.
Next slide. The stainless steel base plate is connected by 3 screws to 2 pieces of 80/20 that attach to the frame of the liquid handling system. The base features small L-shaped and T-shaped locating markers to provide designated locations for each of the items placed on top. The markers will attach to the base plate with adhesive to provide more modularity to the user for future use. These markers allow the liquid handling subsystem to require fewer necessary calibration tests before use of either the pipetting or gripping systems. The base accommodates space for the 2 different sizes of pipette tips, a disposal bin, 3 micro weld plates, and a test tube rack that can hold both 15 milliliter and 50 milliliter conical tubes. There is also a designated location for the lid of the weld plate incubation system. The slot cut into the base plate is for the ventilation of the Bioshade Q1, which sits within the weld plate incubation system. Our device includes a big emergency shutoff button that mounts onto the 80/20 frame. When pressed, this button will safely stop and shut off all the current running functions. The microbioreactor will shut down if either the components are assembled incorrectly or an improper protocol or function is chosen when attempting to run the machine. As an additional precaution, a phone alert will be programmed to be sent out if any failure of cell culture condition is detected. Next slide, please. The user interface panel incorporates the use of a screen to indicate the current various parameters the microbioreactor is running, such as the duration of the cell culturing, temperature, and shaking pattern. Whether the system is on or off is also shown on the panel, as well as if there are any errors present during culturing. The green light located at the top left of the panel acts as an attention-grabbing visual indicator to the user. There is a USB Type-B plug-in component to connect a computer to the machine in order to program all the various functions and modes necessary to set up and run the cell culturing trials. The user interface panel was designed in a way to increase modularity for the user. There are holes on all 4 sides of the mounting bracket so the user can easily attach the panel in their desired location onto the 80/20 frame. Now for an in-depth look into the tube incubation and monitoring system with Stephen.
Our tube incubation and monitoring system is comprised of an aluminum compartment with a lid that has a piece of silica rubber in between that allows for proper sealing. The seal provides an enclosed environment that can maintain the incubation conditions for 2 weeks. Furthermore, the tubes inserted into the system are easily interchangeable. There are gas ports that allow for press-fit connections to solenoid valves, which allow for gas control, and there's an additional port that can capture effluent gases. We chose an aluminum compartment and fins to increase the rate of heat transfer to maintain the correct temperature inside the system and to make sure that the exterior surfaces do not exceed 55 degrees Celsius. Next slide, please. The tube sleeves are made of aluminum and come in 2 sizes to account for the 50 milliliter and 15 milliliter standard tube sizes. The sleeves are situated in a tube holder which is on top of a Peltier module. Thus, the Peltier module has direct contact with the aluminum sleeves and can provide uniform heating under slow temperature changes. In addition, the Peltier module has a temperature range of 4 degrees Celsius to 70 degrees Celsius. The entire sleeve assembly sits on top of a circuit board, which connects all the electronic parts, such as a thermistor, which allows for closed-loop control of incubation temperature. The circuit board sits on an aluminum base, which allows the whole sleeve assembly to sit on top of an OTS shaker, which is represented by the large white box since the company does not provide a CAD model. Next slide, please. The sleeve sits in a tube holder, which contains a filter. The sleeve sits on top of a tube holder. There are 2 holes in the sleeve and sleeve holder, which allow for the placement of an LED and photodiode, which can allow for the measuring of optical density and fluorescent intensity. There is a high-powered light that is located on the lid of the system, which can provide a 640 nanometer wavelength light at an intensity of 1 kilowatt per centimeter squared. This system is not automated because after speaking with the customer, it was determined that the conical tubes have significantly longer periods of incubation compared to microplates. Thus, it was determined that incorporating a method of automating the tube system was not cost efficient in the amount of time that it saved the user. After the liquid handling system fills the tubes with media, the user can then transport the tubes into the system for incubation. Next up is Adriana with the well plate incubation and monitoring system.
Our solution to incubating and monitoring well plates is twofold. I shall begin with explaining our incubator. Our incubation solution involves the usage of a Bioshade Q1, which is an OTS part. This takes care of both shaking and heating and cooling. The bioshaker is placed within an enclosed housing, very similar to that of the conical tube incubator. The housing is outfitted with fins to take care of heat rejection. These fins operate on the principle of a simple heat sink, utilizing increased surface area to dissipate heat away from the enclosed environment. These fins were implemented to ensure that the exterior housing does not reach temperatures above 55 degrees Celsius as requested by the customer. Also, just like the conical tube incubator, the housing features 6 holes on the side. 5 of these holes will be used by press-fit tubes that will handle independent injection of nitrogen, oxygen, carbon dioxide, methane, and hydrogen gases. The 6th hole will be press-fit with another tube connected to a compressor, taking care of gas exhaust. The inlet and exhaust vents of the Q1 bioshaker are connected to holes along the outer housing in an effort to dissipate heat away from the controlled environment. Just as in the conical tube incubator, there's a light that is located on the lid of the system, which can provide 640 nanometer wavelength light at an intensity of 1 kilowatt per centimeter squared. The Bioshade Q1 is developed by Q Instruments. This device can accept 6, 24, 48, 96, deep 96, and 384 size well plates as requested by the customer. The heating and cooling aspect of this device is capable of adjusting the temperature of well plates to a range between -10 to 99 degrees Celsius. This is above and beyond the range requested by the customer, which was a range of culturing temperatures between 4 and 70 degrees Celsius. As claimed by Q Instruments, the nominal regulation accuracy of the Q1 is better than plus or minus 0.1 degrees Celsius, with a uniformity of temperature distribution better than plus or minus 0.7 degrees Celsius at 4 degrees Celsius across the cooling surface. This will ensure uniform well plate heating and cooling to prevent condensation. The Bioshade Q1 also has shaking capabilities built in. Using an efficient two-dimensional shaking axis, this device is capable of linear, orbital, and double orbital shaking patterns as requested by the customer. The orbital speeds are fully adjustable between 200 and 3000 RPMs. The solution to optical density and fluorescent intensity readings of well plates is taken care of by Chow Labs' open source plate reader. The goal of Chow Labs was to create instructions for a plate reader that would be affordable for laboratories or educators in the field to build for themselves and modify as they see fit. We chose this solution for measurements due to the low cost of $3,500 compared to industry spectrophotometers. The reader is capable of performing a full range of optical density and fluorescent intensity measurements on all the sizes of well plates requested by the customer. In order to deliver well plates from the well plate incubator to the plate reader, the grabber arm is tasked with grabbing the well plate from the incubator and placing it on a retractable DVD disc-like tray which extends from the reader. The door features a self-closing spring hinge which opens up thanks to the force of the extending tray and closes again once the tray retracts. Chow Lab states that a full optical density and fluorescent intensity reading of a single well takes 11 seconds, including time moving between wells. This means that a reading of a 384 well plate will take 70 minutes. As stated by the customer, any time outside of incubation past 20 minutes might kill the cell culture. Because the reader is outside of incubation, in order to perform a reading of a 384 well plate, the reading will have to take place over 4 passes, each of 96 wells, with the plate returning back to incubation for a minimum of 10 minutes before the next pass. Now, I'll hand it off to Matthew for a TRL analysis of our independent subsystems.
Now we address the technology readiness levels of our design, broken into the 4 subsystems. We do not address the TRL levels of individual components as most of them are off the shelf and are therefore near TRL level 9. Our liquid handling system consists of an off-the-shelf gripper pipette, which translates along an 80-20 frame. The key elements of this system have been demonstrated numerous times with 3D printers and automated pipetting machines. So our liquid handling system is rated at TRL level 4. Our fail-safe and user involvement requires extensive post-manufacturing programming and control engineering. So the design can only be said to have been formulated conceptually. Rating at TRL level 2. Our conical tube system was demonstrated in computer modeling and mechanical engineering analysis without having been demonstrated in a laboratory environment, rating it at a TRL level of 3. For the very same reasons, our microplate system is also rated at a TRL level of 3. With the component subsystems rated, we arrive at a total product technology readiness level of 2 because of the weakest link analysis of the subsystem integration. With that, Eusebio will take over with an overview of the unique design features. Next slide.
All right. When conducting preliminary research, we found that none of the existing bioreactor designs have all of the features design required by the US Biofoundry. Some had a few customer needs listed, such as the Clavin Lab design that can add liquid, but it does not have the ability to subtract liquid. There were also other designs that did not feature fluorescence detection for fluorescent intensity monitoring, which is essential for the customer to be able to carry out the desired lab experiments. We came across a design called Bio, which has some of the desired features such as fluorescence detection, shaking control, and temperature. They do not meet all the customer needs specified by the US Biofoundry. In addition, the Bio design does not fully allow for the adjustable well plates and test tube sizes required. We therefore came up with the solution to the proposed required product by fulfilling as many customer needs as possible in our final design concept. Our system incorporates the open trunk pipetting devices to be able to aspirate liquid volumes and dispense them accurately in both well plates or test tubes as needed. In addition, we have added a pneumatic gripper mechanism to aid in creating a more autonomous system. Creating a more robust liquid handling system was important to us, as this was something we did not see much in our research. Also, by designing our own liquid handling, we are able to customize it to better suit the needs of our customer. Next slide, please. Therefore, the new system also allows for individual temperature control for well plates and test tubes. We designed 2 separate systems of incubation, one for test tubes and another for well plates. We did so due to the dimensional difference between the two, as it was difficult for us to come up with a design that would be able to individually and accurately measure optical density and fluorescent intensity ratings in one single design. Therefore, choosing this route also helps us fulfill the customer need that requires for an incubation period of up to 2 weeks, in which case the system can perform more culturing in the vacant closed compartment. Next, Matthew will cover our design costs and other further details.
Now we come to our cost analysis. Our hedgehog concept specified autonomy, which when combined with our aims of modularity and high individual component technological readiness, this led to a large volume of off-the-shelf parts and associated expense of about $13,000. If we look at our design as a spatial map of cost density, we find that our off-the-shelf well plate reader, our off-the-shelf well plate thermal shaker, and our liquid handling subsystems are high cost concentrations at around $3,000 each. Our custom parts are primarily made of 316 stainless steel, aluminum, and polystyrene, which we use to arrive at our total raw cost of about $2,000. Associated with these materials, we also have a significant amount of manufacturing to do for our custom parts, particularly machining, casting, and injection molding. So there we arrive at a non-negligible manufacturing cost of about $1,000, which was found as the total hours of required manufacturing time multiplied with the hourly wage, including benefits and overhead, to employ an average manufacturer from across the relevant specialties. This machine, our assembly labor costs stem from this also the standard rate of $56 an hour, which is the same for assemblers, to employ an assembler for about 2 hours. which was the total time found from the assembly from Boothroyd and Dewhurst insertion and handling estimation techniques. With that, our estimated cost came out to about $16,250. Next slide, please. Why should our design be selected for design 3? Next slide. So undoubtedly, the panel has noticed some glaring points about our design. We are 60% over budget. We can't fill larger well plate volumes in one pass. Our design is not visually appealing. And our conical tube support is not completely automated. Why should our design be selected with such negative qualities? Our negative qualities are actually a consequence of our very attractive points of our design. Our price is a consequence of how easy, modular, and cleanable our product is. The design can essentially be broken into almost all of its constituent parts with ease. And the design is very customizable for the various user environments that might be seen in each independent laboratory. This is especially seen if you recall the modularity of our user involvement and fail-safe systems. Our inability to complete larger well plate volumes in a single pass is a result of our use of off-the-shelf parts, which results in a lower individual technology risk level in each component system due to the proven success of the individual parts and their simplistic integration. Similarly, our visual unattractiveness is a consequence of allowing the greatest amount of degrees of freedom for our automation system. Our conical tube support lacks automation only in transporting tubes from liquid handling to incubation, which is easily, safely, and quickly done by an experimenter in less than a minute. Since the tube cultures are meant to be exposed to longer incubation times of those on the customer needs statement ranging up to 2 weeks, this lack of automation is negligible and spares the design further cost overruns and maintains a smaller, more modular framework. Next slide, please. Now we're going to wrap up our presentation with a small overview of the product. Our design is based around autonomy, and our chief goal was the autonomous microplate handler, prepare, incubator, and reader. And we have achieved that through our unique gripper pipette arm, isolated culturing environments, minimalist USB user interface, tube culturing sleeves, and thermal shaking unit. Our design is superior to others in its minimal user involvement, high modularity and cleanability, and low individual component technology risk. Next slide. Thank you for your attention and patience, and we now open up the presentations to questions from the panel.
I have a quick question. What is the overall weight of the system?
The weight of the system, I think Stephen was the last one. It was you, Stephen, who ran the mass properties.
I do not have a fixed number for that, sorry.
Okay, all right. The weight should be in the order of 80-20, say about 40 pounds, just as a ballpark estimate. We did run the mass properties, but we don't have the number with us. Apologies.
Thanks. Also, I was wondering if you did any stress analysis on that angle gripper. How thin is that, those pieces, those arms, and did you think about like where it would fail?
With that, I'll turn it to Ariana. She's the expert on the gripper.
Yes, it is about 3 millimeters in thickness. It is aluminum. I kind of thought about what kind of weights it would be lifting, which is the well plates, and it is well supported, so I did not foresee any, stress failures there. We did perform FEA analysis on the 80-20 support brackets, but now that you mentioned the angle gripper, that's probably a good idea for the final design report. But I don't foresee like any stress, significant stress concentrations anywhere. It is well supported by, I think, 4 screws on each one. But yeah, hope that answered your question.
So I would suggest, since you mentioned it, that FEA on your 80-20 is way overkill. And I mean, I know it makes pretty pictures, but it's much more reasonable to just do a hand calc. Especially if you're talking, you have a large factor of safety. I think that's perfectly, reasonable thing to do. The gripper itself is the weight of the trays doesn't seem like the main thing. It's more the force that's being applied to the size of the trays is what's going to create loads on that gripper.
That's a good point you bring up. We'll definitely take that into contention.
Yeah. Keep on
Sorry,
going.
go ahead.
I was going to say, on the same note of 80/20, did you, like, if you are going to do an FEA analysis for 80/20, like, do you account for the bolted connections in any way? Because how many of you guys built a robot in DML where after the first run, you literally picked it up, went back to the desk, and twisted the frame to get it to line back up again? Like, you can do a structural analysis of it, but if you're missing out weak, soft interfaces, it's not going to be accurate anyways at the end of the day. So that was just my other point to jump on the 80/20.
Yeah, without a frame on this thing, it's going to rack, it's going to twist, it's going to move all over the place.
Yeah. I mean, you're missing, from what I see here, you've got like 2 angle brackets in each corner. For 80/20, to get that thing stiff, you need like 20 per corner. There aren't enough angle brackets you can put on to properly constrain 80/20. So, but
Also, what was the weight of that middle like gripper / pipette system, and can that linear actuator lift that entire system?
How do you have the numbers for those?
Yes, I do not have the weight. It is not very significant. I think the most, like the heaviest part is like the stepper motor and the pipettes together, which is about 1 pound. And the motor that controls the system is high torque, so it should be able to move everything without a significant problem.
Let's talk about your heating and cooling. You've got boxes that are sitting inside of finned enclosures, which appear to be entirely passive. And you mentioned that you've got Peltier plates that will get you, a range of 4 degrees to 70 degrees. I'm wondering, with the heat transfer in and out of those, are they going to be able to meet that range? And if you're getting hot in there and all your heat is just being dumped to the outside by these fins, you're going to have to dump a lot more power in to maintain the temperature inside.
Alex, you're a heat transfer guy. You want to hop on that one?
Yes. So for the heat transfer, there has been extensive redoing of calculations for this. The inside fins are meant to, not a lot of heat transfer actually goes to the inside fins for small incubation times, because it takes a long time for the heat to transfer over what is essentially, it's not a vacuum, of course, it's a gas, but slow gases. So that doesn't take very long for that. So unless you're incubating for a long period of time, most of the heat transfer out actually goes through the base, and then it goes to the outside through the outside fins. As far as maintaining temperature at it should not have a problem as long as for the small incubation times. For the longer incubation times, where the ambient air is actually being heated in the steady state to the same as the cell cultures, then you run into more of a problem with this. But the calculations have shown, especially with the conductivity of the aluminum and with the conductivity of the aluminum and the properties of the air, or whatever gases you have inside, it does not change very quickly. And you can supply more power from the Peltiers, the Peltier modules, to accommodate for the increasing loss of the temperature through the inside fins for longer incubation times.
So what are these fins doing for you exactly?
They allow us to get the heat out, since we have essentially what is a refrigerator in a box, the classic thermodynamics problem. We have heating elements inside of a small space. And so we need to, when we start cooling the design, we need to get the heat out.
If you just told me that was a very inefficient way of doing that.
I'm sorry, could you clarify?
You just said that you don't get a lot of heat transfer across those fins.
No, not for small incubation times. We rely mainly through the conductivity through the base and then out through the outside fins.
So I don't think I have an answer to my question.
Could you, I'm sorry, maybe I'm not understanding your question.
If you don't have very efficient heat transfer, most of it's going through the base, what are the fins doing for you?
The fins are there for the longer incubation times when the temperature has had enough time to actually go through into the ambient air inside of the incubator. It's sort of a multi-stage system depending on what kind of incubation study you're running.
All right.
Do we have any more questions from the panel? Okay, wow. Okay, so seeing no more questions, we'll wrap it up there. And interestingly, that puts us almost back on track. So so let me stop recording.